In this video, we are going to take a look at dividing monomials together and some of the properties that go along with that. Big thing to remember with this entire section is that we are essentially just reducing fractions that contain monomials and variables now within them. So a lot of the different properties that we used previously for simplifying and working with exponents are going to be showing up here. And that's mainly because when we have monomials multiplying or being raised to powers or being divided by one another, all of these previously learned properties are going to come into play with these new problems that we're going to be seeing. We're also going to be seeing problems where we need to maybe do some of these previously learned properties before we can actually work with some of our newer properties that we're going to be going through and covering today. So if you haven't, I would highly recommend writing down the product property, the power property, and the product to a power property for yourself before we go into this next part here and we move into our example problems. These are review from our previous sections and previous videos that we've covered. Now, the new material, the new properties that we have at our disposal. We have the quotient property, and this states that if I have a non-zero base that is being raised to the a to the m power, being divided by a to the n power, something like we have right here, then we have one of two scenarios showing up. If the numerator is greater than the denominator, then that means that the exponents are going to subtract, and the answer will be in the numerator. If the denominator is greater than the numerator, then if I have a situation like this showing up, I'm going to once again subtract these exponents together, but I'm going to instead do n minus m, the larger number, which is the denominator, minus the smaller number, which is the numerator, and the result will end up in the denominator. So whichever part, the numerator or the denominator, had a larger exponent, that is where our final answer is going to be once we are finished doing subtraction. We do cover in the 6.7 material how to work with negative exponents as an alternate way of going through and working with the quotient property, but we'll save that for that specific section. We might see a little bit of that show up here today, but we're going to primarily use this version and these properties or ways of going through the quotient property. Our next one that we have is the zero exponent definition. And this states that if I have any non-zero variable or number raised to the zero power, the result is always going to be 1. A lot of people have the misconception that if we have a base raised to the zero power, that the answer is going to be 0, much like when we have 0 multiplying with something. However, this is not a base multiplying with 0. This is something raised to the 0 power, a completely different operation. We will see two ways that this can end up happening in a problem, and I think that should help see, well, why is this property always the case? And last but not least, we have the quotient raised to a power property, which says if I have a fraction, something like a divided by b, all contained within a set of parentheses, and that set of parentheses is being raised to some exponent power, n in this case, then that's equivalent to raising the numerator to the m power and the denominator to the m power, and then simplifying them down respectively from there. It's also assumed in this case that the denominator, b here, is a non-zero number, so that we're not dividing by 0. So these are our three main new properties that we're going to be covering and seeing in this 6.5 material. But again, our first three, product property, power property, and product to a power property, they're all fair game. We will be seeing those in some examples later on down here. Now it should be noted as well that when we are going through and simplifying a lot of these problems, PEMDAS, the order of operations, governs our process and everything that we do. We do have some options to slightly deviate from the order of operations, and we'll see that with some examples later on. But if you ever are wondering what to do, fall back on PEMDAS and let that guide you through these problems. Should also be noted that all of our previously established rules for fractions, for adding, subtracting, multiplying, and dividing them together, they still hold true even if numerators or denominators do contain variables. Those properties and those rules and all of that are still the same and still established here. Still also means that we need to have a common denominator for only adding and subtracting fractions. A lot of people get the idea that we need the common denominator for multiplication and division as well. Just as that reminder, a common denominator is only required for addition and subtraction with fractions. So we have 8 examples here that we're going to take a look at and see all of these different properties in play here. We'll start off with some maybe more straightforward examples up here with 1 through 4, and then 5 through 8 is where we get to some of the more advanced stuff and really see how we can mix and match some different properties together to simplify a problem down. So with that, let's go ahead and dive into and see how we go through and solve these. Looking at our first example, we've been given the fraction x to the 43rd power divided by x to the 38th power. This is going to require us to use the quotient property, where we have a base raised to a power divided by the same base raised to a different power. Okay? Now we are noticing that the exponent for the numerator, 43, is larger than the exponent for the denominator, 38. That means that my final answer when I subtract these exponents together is going to end up in the numerator spot. So I can go ahead and write this out for myself as x to the 43rd minus 38 power. Again, the exponents are subtracting here. I can go ahead and subtract those, and I should be getting x to the 5th for my final answer. Again, we're noting that the numerator has a larger exponent attached to it, so my final answer that we have here ends up being in the numerator of that fraction as well. Looking at our second example, we're given n to the 3rd power divided by n to the 7th power. In this case, we once again have the bases the same, and they are dividing, the numerator divided by the denominator. But in this instance, compared to the first one, we notice that the denominator has a larger exponent, therefore meaning that our final answer when we subtract these exponents is going to end up in the denominator spot of our fraction. So that means we can write this out. Oops, I should probably use an actual pen version for this. There we go. So I can rewrite this to be 1 over n to the 7 minus 3rd power. And when I go through and actually subtract these things together, I'm finding that I'm getting 1 over n to the 4th power, just 7 minus 3. So make sure when you are working with these quotient properties and things like that, before you actually do the the subtraction, I should say, make sure that you are taking time to notice which spot, the numerator or the denominator, has the higher exponent value, because that's going to determine where your answer is going to end up, either the numerator or the denominator spot. Our third example here gives us something that's a little bit unusual to look at first. We have y to the 11th power divided by y to the 11th power. Now we have 2 ways that we can think on this and go through and get to our final answer here. And I want to show both of them because I think it really highlights the zero exponent property and how that comes into play here. So let's apply the quotient property first. I have the same base, y, that's being divided by itself. Okay, that means I can go ahead and use the quotient rule. And that means I'm going to get y to the 11 minus 11 power. Now when I subtract those together, I'm going to get y to the 0 power. And as we have with our previously established rules, any non-zero base raised to the 0 power is going to give us an answer of 1. So this thing ends up being 1 for final answer. Now, again, we're looking at this and you're still looking at this thinking, well, okay, something to the 0 power is 1. That still seems weird. I'm not exactly sure how. Let's take a look at it a slightly different way and see if this might help. If we were to have this exact same problem here, I have y to the 11th divided by y to the 11th, we effectively have the same thing being divided by itself. I have whatever the numerator is divided by its equivalent thing in the denominator spot. Anything divided by itself means that these things cancel out and they each become 1. So this will ultimately reduce down to being 1 over 1, and 1 divided by 1 is just going to be 1 again. So hopefully this gives a little bit of a highlight or an insight as to how we have something raised to the 0 power equaling 1 for our final answer. But again, if we see anything divided by itself, we're more than welcome to just jump right to a final answer of 1 and not have to write all these extra steps in along the way. Looking at our fourth example, we have the fraction 5 over 7 inside of a set of parentheses, and those parentheses are being raised to the 3rd power. So like we did with example 3, I want to show two ways that we can go through this. Both are perfectly valid, though I think one is going to be a little bit more efficient and take up a little less time than the other. But I do want to show that there are multiple ways to go through this. So let's use our quotient to a power property that we just learned. That states that if I have a fraction raised to a power, the entire numerator is raised to that power and the entire denominator is raised to that power. So this thing ends up becoming 5 to the 3rd power divided by 7 to the 3rd power. We can use our calculator off screen, that's what I'm using, and do 5 to the 3rd, that's going to give me 125, and then 7 to the 3rd, that's going to give me 343. And once again, check to see, can I reduce this fraction down? We always need to check that, and no, it turns out we cannot, so here we have our final answer. Now, as an alternative method that we could use, this is not relying on our exponent properties that we're learning. It relies instead on us expanding and multiplying these things together. It's perfectly valid, there's nothing wrong with it, but I'll let you be the judge of if you want to use this method or not, because I think it takes up a little bit more space than we might like. So if I were to go and expand this thing out, I would have 5 over 7 multiplying by itself 3 times, just by our exponent definitions here. So we write this out a few times, and there we go. Now we multiply two things together at a time. We get 25 over 49 for our first part. Oops, I should probably actually write in 25. There we go. Or 49, and then I multiply it again with another 5 over 7, and that's going to give me this 125 over 343. So both methods are perfectly viable, both methods work, they get us to the exact same answer, but the properties that we just learned might make this a little bit faster, especially if we are using a calculator to go along with those. And if you are watching this and you are in my class, you are more than welcome to use a calculator to go through and do this calculation for yourself. Perfectly valid. I'm all for doing that for the homework and for the tests. With example 5 and moving on to our final 4 that we have here, we're going to start seeing problems where we are going to be viewing and having to use multiple properties to get through and simplify a single expression that's been given to us. Now, my recommendation is that you do these things in very small, very controlled, very precise steps. A lot of people, understandably, want to do 2 or 3 or 4 things at once with these problems, and they might correctly identify all of the properties that we are going to use, but we do them in an incorrect order, and that's where things go horribly, horribly wrong with our problems and getting to our final answers. So let's think on this problem here in one route that we could take. I have stuff going on in the numerator. Specifically, I have the power rule showing up. I have a set of parentheses raised to the 4th power, which means that something's going to happen with these two exponents here. I also have in the denominator m to the 7th. Now the numerator also has an m, but I need to work with this set of parentheses and this exponent first before I can work with the quotient rule later on. I also recommend to people when they're going through these is just simplify the numerator all by itself. Just simplify the denominator all by itself. Then and only then do we bring problems together and see what the quotient rule might do and reveal to us. That's just an option that you can use. There's nothing wrong with it. I think it's going to be helpful here, and we'll see in some other problems where we may or may not use that. So here, let's work with just the numerator first. Whoops, I keep using this highlighter thing. Let's switch it off from the last problem. There we go. So I have in the numerator, I have m to the 5th being raised to the 4th power. So that, using the power rule, that tells me that the exponents are going to multiply, and I'm going to get m to the 20th over m to the 7th. So I've just done one thing, but hey, it's already looking a little bit simpler than it did before. Now I can use the quotient rule, and I have more m's in my numerator spot, or my exponent in the numerator spot is bigger, and that tells me that my final answer is going to be in the numerator as well. So that means I'm going to get m to the 20 minus 7th power. So 20 minus 7, that's going to give me 13, and I have a final answer of m to the 13th. Now again, this is where we're getting just an early preview of some of these more advanced problems, but notice how we're doing just one thing at a time from one step to the next. If you want to rush these steps, you're playing with fire, and I feel like a lot of errors tend to show up if we try and do 2 or 3 or 5 things all at once. So be careful with that as we're going through our next few problems. Now with our 6th example, we're going to start seeing problems that are going to get a little bit more complex, and there's a lot more that's going on with them. So we need to make sure we're being, again, very precise in what we're doing from one step to the next. So we have a fraction here inside of parentheses being raised to the 3rd power. This tells me that of our new properties, we're going to be using the quotient to a power property, which says I'm going to raise the numerator to the 3rd power, and I'm going to raise the denominator to the 3rd power. So let's go ahead and rewrite this thing first before we actually apply any properties here. So we have this showing up with our rewrite. Now we could go a step further with this as well and say this numerator is a product to a power now. So I could go a step further with rewriting this and make it even clearer what's happening to each number, variable, and all of that. I'm going to end up having -2 to the 3rd power, and I'm going to have y to the 4th raised to the 3rd power. In the denominator, I have just the power rule showing up. It's already in its kind of simplest form for now, but now I have everything written out in the product to a power. This is just going to be the power rule. I'm getting all of them mixed up. I'm looking at a different screen and I'm getting all the different words jumbled up. So now that I'm going to say it properly, hopefully for the rest of the video, probably not, but we'll see, I can work with -2 to the 3rd power. We can plug this into our calculator if we wanted to, and -2 to the 3rd power is going to give us -8. Y to the 4th raised to the 3rd power, that's going to have us use the power rule, which means these two exponents are going to multiply together, and that's going to give me y to the 12th. For our denominator, we once again have the power rule showing up. We have x to the 2nd raised to the 3rd. These exponents once again multiply together, and we get x to the 6th power. Now at this point in time, we're looking at the fact that we have variables in the numerator and the denominator spot. Could we apply the quotient rule here? And while it's tempting to want to do that, we actually cannot. The bases of these exponents, in this case the y and the x, are different, and therefore, because the bases are different, I cannot do anything with these exponents. They're going to stay exactly as they are. Which, the nice part about that, means we have our final answer. It's fully reduced down. There's no numbers that can or coefficients that could reduce, so we're good to go. We have a final answer of -8y to the 12th, all divided by x to the 6th. Looking at example 7, we have a really gross looking thing here. We have the quantity a squared raised to the 3rd power, the quantity a squared raised to the 4th power, and then that is all being divided by the quantity a to the 4th power being raised to the 5th power. So it's kind of gross, it's kind of a mess, there's a lot of properties that are showing up here. My recommendation is you take this, once again, very slowly, very steadily, and be very decisive with what you're doing. I'm going to work with just simplifying the numerator first. So I'm just going to write this up for myself. So I have my numerator. Let's just rewrite that thing down below here. A lot of people do not like to do these steps because they feel like it's taking so much extra time to write it out, and maybe they're right in that it's extra time to write things out, but I think it makes it much clearer what we're doing and how we're getting to our answer. So if I'm looking just at this, I'm noticing I have things multiplying together here with the parentheses. And I also have the power rule showing up here. An exponent raised to a power, another exponent raised to a power. So let's start with the power rule because that's what PEMDAS, our order of operations, says to do first. We work with exponents before we work with multiplication. So with our first part here, we have 2 times 3. That's going to give us a to the 6th power. And that's going to multiply then with a to the 8th power. Now that I've taken care of the exponents multiplying here, I have 2 bases that are the same and multiplying, which means I can use the product rule. So that's going to give me a to the 6 plus 8th power, which gives me a to the, which equals a to the 14th power. Perfect. So our numerator is now as simplified as it can be. Let's take a look right next to that at the denominator. So if we work just with the denominator, let's write that in. We have a to the 4th being raised to the 5th power. And here I'm just using the product, not the product, the power property. I thought I was going to mess it up one more time. I probably have a couple more times here. So I have the power rule, a to the 4th raised to the 5th. These exponents are therefore going to multiply together. And that's going to give me a to the 20th power. Now that I have my numerator fully simplified and I have my denominator fully simplified, let's bring those together and rewrite it right over here. I'm going to make one more column for myself. And we'll just title this column as rewrite. So I'm now going to have a to the 14th power over a to the 20th power. Much nicer to look at, and I think it's much nicer and easier to keep track of what we're doing along the way. Otherwise, you're kind of applying the power rule here, kind of applying the power rule here. Am I applying quotient rule yet or no, or all that? It can be an absolute mess if we're trying to do it all at once. Now from here, I have 2 bases that are dividing. They are the exact same, which means the quotient rule is in fair play. The denominator has the larger exponent, which means my answer is going to go in the denominator spot. So I can set up my answer now and say I'm going to have 1 over a to the 20 minus 14th power. 20 minus 14 is going to give me 6, which means I'm going to have 1 over a to the 6th for my final answer. Now while I went through and split this thing up into numerator and denominator, you could do each of these steps inside of one big fraction. You would just want to wait to use the quotient rule until you have the numerator and denominator fully simplified. So you can do them all at once, then get to here and simplify, or separate them out and do them individually, then bring them together and simplify. Either route would work. And here we are at our 8th and final example for this video. If we're looking at this, yeah, it's kind of a mess. There's a lot going on here. There's a lot of variables. There's a lot of properties. And it can be a bit overwhelming of what we want to do, how we can start this thing or not. So I want to start off with saying that you have multiple routes that you could take to start this problem, but they will all ultimately lead you to the same final answer. Me personally, I like to simplify the numerator all by itself, simplify the denominator all by itself, and then look to see what I could do and simplify in the numerator and the denominator spot. Essentially then cancel stuff out. I have found for me personally, I look at these and I would say, hey, the negative 12s might cancel, but wait, this negative 12 also cancels with the negative 4. Or this x to the 6th and x to the 10th, they kind of cancel, but then there's this x to the 5th which multiplies and it adds. And if you're losing track of what I'm even saying as I'm talking about that, that is reason enough right there to do these things in separated parts. So let's look at just the numerator here. I have coefficients showing up. I have negative 12 and I have a negative 4. Let's just multiply those two things together first. So negative 12 times negative 4, that's going to give me a positive 48. I then have x to the 6th multiplying with x to the 5th. That's going to use our product rule, which means that the exponents will add together. That's going to give me x to the 11th power. I then have my y's, and I have y to the 9th times y to the 8th. Again, the bases are the same, and the bases are multiplying, which means the exponents will add together. And that's going to give me y to the 17th power. Try and move this little blinky guy off to the side. There we go. Now, I've not done anything with my denominator at this time, so I'm just going to bring that down exactly as it is. And I want to note something before we move on from here. What's nice about this strategy, simplifying the numerator first, then the denominator, and then we cancel stuff out, how many x's did I have up here before? I had two different things with x's. I condensed it all down to be one single x value here. Maybe it's nicer, maybe it's bigger, maybe it's smaller than what I had originally, but it's just a single x. Same thing with y, and same thing with our coefficients. So I have coefficients aligned here, I have just x's here, and I have just y's here. We've condensed each thing down individually, so now it's much nicer to look at and say, hey, what am I doing here with my coefficients? What am I doing with my x's? And what am I doing with my y's? It's much nicer to look at in that regard. So let's go through and actually do this now. So we have 48 divided by negative 12. Those things are going to cancel out and simplify down. 48 is going to become a 4. The 12 is going to become a 1. We have x to the 11th over x to the 10th. The exponents are going to subtract, and my result is going to be in the numerator spot. So I'm going to have just a single x to the 1st left over. Then I have y to the 17th divided by y to the 12th power. And again, the exponents are going to subtract, and the answer is going to be in the numerator spot. So I'm going to have a 17 minus 5, or minus 12 is going to give me 5. I'm going to have y to the 5th left over. Let's rewrite this down below here. And again, this is just one way you can write it out. But we're going to have x, or negative 4, times x to the 1st power. We don't need to write that invisible 1 in there. It's not necessary. And then we have y to the 5th left over here at the very end. Now you could, off to the side over here, do each of the exponent or the quotient properties on their own. Maybe you did x to the 11 minus 10 gives me x, and then y to the 17 minus 12 gives me y to the 5th. Maybe you had to do this step off to the side for yourself. And if you have to, there's nothing wrong with that. Do that as much as you need to, as long as we bring it all together here for our final answer. Make sure you're also keeping track of which spot, the numerator or the denominator, has a higher exponent, and that's going to be determining where your final answer here is going to end up. But because we have everything in the denominator canceling out to 1, everything is therefore left over in the numerator spot, and we have our final answer of -4xy to the 5th power. As a recap of everything we covered in our video today, we were working with dividing monomials, and effectively we were just reducing fractions down that had monomials inside of them. We used our previously learned product power and product to a power property, and we had 3 new ones showing up: our quotient property, our zero exponent definition, and our quotient to a power property. Remember that when we are simplifying these things down, at the end of the day, we are using PEMDAS in our order of operations to go through this entire process. We also went through these 8 examples that we had here. I really emphasize and really encourage you to try from, if you have complicated stuff like 5, 6, 7, and 8, try just simplifying the numerator all by itself, then simplify just the denominator all by itself, and then bring things together to simplify and use the quotient property, like we did with number 8 here. I think that makes these really complicated looking problems, like 7 and 8 in particular, much more easier to manage, and at least make it feel like we have a chance of getting to the start to the end. Lastly, I have a few extra problems if you would like to try any of those. Again, I recommend pausing the video here, giving these a try for yourself. We'll scroll down to our final answer. Answer selection right down here. Hopefully you are getting the exact same thing as what's written in our answers here. If you are having some headaches, specifically with the group 1 number 1 and group 2 number 2, I would recommend rewriting these two things as fractions. Here's my numerator, here's my denominator. This whole thing inside of brackets is a numerator, and this whole thing inside of parentheses is a denominator, with the division sign separating them. So if you got those wrong, try rewriting it like that. See if you can get the same final answer here. But otherwise, that is everything for our material working with dividing monomials.